Hello everybody, my name is Adam Maloney, and this is my final project for MECH 3230, Control of Automated Systems. Today we're going to look at Proportional Integral Derivative Control, or PID control for short. This is an instrument which has been used by control engineers to regulate process variables within industrial control systems. The two main types of PID control tuning are the Ziegler-Nichols tuning method and the Cohen-Kuhn tuning method. The Ziegler-Nichols tuning method may be used for both closed and open-loop systems. However, the Cohen-Kuhn tuning method may only be used for open-loop systems. There are also other types of tuning methods. One is the manual tuning, which is done exactly as it sounds, via trial and error by a person manually tuning. There is also auto-tuning. Auto-tuning is automatically done via the computer. Oftentimes, though, auto-tuning is unrealistic and cannot exist for mechanical systems. PID control is used throughout the world in applications requiring accurate and optimized automatic control. An ideal or perfect PID control will result in a steady-state error of 0%. There are some issues with PID control, though. While extremely effective, the PID algorithm does not guarantee complete optimal control of the system or its stability. Unfortunately, there are situations that may occur where there are excessive delays in the system. All of these will result in larger steady-state errors and an imperfect PID control system. Here we have an example and the method of the Ziegler-Nichols tuning. Please do remember that the Ziegler-Nichols tuning method may be used for both open and closed-loop systems. Here we have an example and the method of the Cohen-Kuhn tuning. Please do remember, though, that the Cohen-Kuhn method may only be used for open-loop systems. Now we're going to demonstrate a PID control system. In this case, we're going to attempt to balance a two-wheeled bicycle. We're going to do this in 3 steps. The first step is modeling. We're going to model the problem and obtain the equations of motion. Then, using the equations of motion, obtain the state space equation. The second step is going to be the Ziegler-Nichols. Due to its ease and accessibility, the Ziegler-Nichols method is going to be the chosen tuning method for controlling the two-wheeled bicycle. Then finally, we have the third step, Simulink. Once we have all our k values, we can move over to Simulink to model the response of the two-wheeled bicycle with the PID controller. From there, we may make small adjustments so as to account for unexpected variables. Here we have all our variables and our free body diagram for the two-wheeled bicycle. Using the free body diagram, we are then going to model the problem and obtain the equations of motion. Once we have the equations of motion, we're going to obtain the state space equation as well as the transfer function. Using the Ziegler-Nichols tuning method, we're going to obtain all our k values so that we may make our PID control system. In Simulink, we're going to test our control system against a regular pulse, which will throw the system off of balance. As we can see here, the PID control system does not hold up past the second pulse. This indicates that a little bit of work needs to be done. Unfortunately, there are times where one needs to manually adjust the PID control. In this case, reasons that may have caused the need for manual adjustment could be the following: noise, ignored variables such as friction and inertia, as well as small angle approximation. In Simulink, we may adjust the k values until a desirable PID control exists. After adjusting the K values in Simulink, we may now observe that the bicycle holds up quite well against the regular pulse. As good as a PID control is, it sadly is not without its faults and weaknesses. Saturation, wind-up, noise, bias, and nonlinearity may all corrupt a PID control, with noise being the greatest offender. Situations may occur where there are excessive delays in a system. The measurement of the process value is delayed, or the control action does not apply quickly enough. All of these will result in a larger steady-state error and the destabilization of the system. This is the end of our lesson on PID control systems. Thank you all so much for your time and have a great day.